about today is how you can optimize your product development cycle using both 3D printing and traditional manufacturing such as injection molding to help accelerate the process for your product success. A little bit of background about me: I've been in the custom quick turn manufacturing space for about 20 years. Starting out with a small company out of Atlanta called Quick Parts, which revolutionized additive manufacturing with online instant quoting, and working up through the years with companies such as Xcentric, where I am now, so focusing on both traditional and additive manufacturing processes. Today we're going to be we're going to be going through, there we go. Today we're going to be taking a look at some of the advantages and disadvantages of both 3D printing and injection molding, and how we can leverage both of these technologies for your product development to accelerate the process and get your product to market on time and under budget as effectively as possible. And then we'll wrap up by taking a look at just a few examples of experiences that we've had with customers where we've used both of these technologies effectively to serve their specific needs. So additive manufacturing, or 3D printing, which is oftentimes called, and injection molding are not competitive technologies. They both serve the prototyping element of your product development cycle very effectively and complement each other quite well. They're definitely used at different stages of the process though, so we're going to dig in a little bit more on that and take a look at how they complement each other really well. So to start with, some of the advantages and disadvantages of each type of technology. So 3D printing, or additive manufacturing, is great for quick iterations. You can have a part built in as fast as a day, get it to you in 2 days, and you can do a lot of iterative design process to really iron out what you want your fit and form to look like for that specific part. You have relatively low upfront costs. You don't have any capital equipment that you have to purchase or assets that you're having to purchase like you do with injection molding. There's not a tool there. You can basically just submit a CAD design, print it really quickly, get part in hand in a couple of days. So they're great for fit, form, and even some functional testing, but there are some limitations there that we'll talk about in a minute. With additive manufacturing, it's great if you have very complex designs that don't really have a way to be manufactured using traditional technologies such as injection molding or CNC machining. So even for production environments, if you have really complex designs, there is an opportunity to be able to use 3D printing for that as well. Some of the challenges with 3D printing is typically is a lower fidelity manufacturing process than what you see with injection molding or CNC machining. There are a tremendous number of materials that are available now from a lot of different vendors, but there are still some limitations in terms of the materials that you're going to get and the functionality of those materials. They're not necessarily going to replicate specifically what you're going to see with a traditional thermoplastic like you would see with injection molding. And additionally, even though it's a great technology to be able to prototype your designs early in the process, there are some challenges, potential challenges where it doesn't necessarily translate to what the part's going to look like or feel like in a production environment. So it's great for that initial fit form, even some functional testing, but it doesn't necessarily mean it's going to be exactly like that in your production environment as well. The throughput is a lot lower. You can certainly stack your builds in an additive manufacturing process where you can build 10, 20, 30, 50 at a time. But when you start talking about making thousands of parts, typically it's not going to be a great technology for that because your unit cost is going to end up being higher in aggregate than what you see with traditional manufacturing processes, mainly because of the build time and the finishing time that's going to be associated with those. So typically the cost is going to be impractical once you start getting into the larger volumes that you're looking for. With injection molding, on the other hand, you have a much lower unit cost that you're working with. You have a much shorter cycle time. You can run a part in 30, 45, 60 seconds compared to the hours that it may take to build your part. And you get actually even in a prototype tool where you're using an aluminum tool, you can actually test the fidelity of the part itself that you're going to be seeing in a production environment, because it's going to be very, very similar to what you're going to be using there. So high flexibility with different materials that you can use. Pretty much any thermoplastic can be injection molded. It's just a matter of making sure that you're working with a partner that has the capabilities to be able to use that specific material that you're looking for. And aluminum tooling specifically is actually a great option for bridge tooling while you're working on production tools. Production tools can take months to produce, especially if you're talking about hot runner systems and multi-cavity class 101 molds. Those can take forever to get off the ground. With an aluminum tool, you can get a tool cut, single cavity, in as fast as 5 days for most relatively simple designs. So it does allow you some efficiency to get product to market a little bit more quickly than what you see in a production environment. There are obviously some cons using aluminum tools for prototyping. You do have the cost of making the tool, whereas with an additive manufactured part, you can print it, have the part in a day, a couple $100, but with a tool, obviously, it's going to be a little bit more expensive on the front end. So you do have to keep that in mind as you're going through the design process. And we're going to talk about how these two technologies can marry together to be able to serve everything that you need in the product development cycle to make it as cost effective and as efficient as possible. One of the things I do want to caution you about with injection molding specifically is that before you get to a place of making a tool, make sure that you're partnering with somebody that can actually provide you with design for manufacturability feedback on your design before you start cutting steel or aluminum. It's really important that you start early in the process, so you're having those conversations even before you're prototyping, just so you know exactly what to expect in a manufacturing environment. Because what happens is with a tool, especially if you have a design where you need to remove plastic, it can end up being really costly and time consuming because you either have to recut the tool or weld it up and recut those specific features. So just make sure that you're working with somebody that's going to be able to support you through the entire product development cycle on the front end. So taking a closer look at 3D printing specifically, usually this is going to be used for evaluating the feasibility of the design that you're working on, looking at what you're looking at as appearance or the feel of the actual CAD data that you've been working on. So again, great for fit and form, some functional testing. It's not going to give you the actual end-use material that you're going to use in production. So typically, the material properties that you're looking for shouldn't be a high priority at this stage unless you have some very specific testing that you need to do, which is when you'd want to consider other technologies to be able to produce the parts. Typically, again, volumes are always a consideration with additive manufacturing. From a cost per unit perspective, the more parts that you need to build, the average cost per part, there's usually a transition point where it makes a lot more sense to go with a traditional manufacturing technology such as injection molding versus doing prints, just because the average unit cost is going to be a lot higher. There are a tremendous number of printers that are available, both commercial and industrial. As you guys walk around the show, I'm sure you've seen plenty of the printers that are out on the floor out here. Relatively low-cost printers are available. There are some challenges that we'll talk about in a second with building the additive manufactured parts yourself that you have to keep in mind. And then also another often used element for 3D printing that I mentioned earlier as well is that if you have a design that just can't be manufactured in any other way, or if you have custom manufactured parts that are individual on a case-by-case basis. So a good example would be like hearing aids. So hearing aids are typically going to be molded to an individual's ear, so you're not going to make a tool and have a standard size shape that you're using for hearing aids or even dental applications such as like Invisalign. I know they use stereolithography for all of their molds that they're using to create the thermoform parts. So that's a great example where 3D printing can actually be used in a production environment and create a lot of value for a customer because you don't have to build traditionally manufactured tools or parts for those custom applications. There are some things to be considered that you want to be cautious of when you are using 3D printing though. Again, it's not great for large part runs. If you're making 500 of something, there are a lot more cost-effective options that you have available to you. There are certain materials that can't be printed. Again, hundreds of materials on the market that are available across dozens of different technologies, but they're not going to be the exact same thermoplastics that you're going to get in an injection molding application. So you can get something that's ABS-like or nylon, or even some nylon-based materials in powder bed technologies, but it's not going to function or act the same as molding a nylon part as you would in an injection mold. So it's a lot different. You have to be considerate of that. Generally, you are limited to build sizes. There are some industrial printers that have really, really large platforms, so you can make a part that's a couple of feet long or a few feet long, but generally speaking, you are still limited to that platform size. So if you need to make 5 of that really, really large part, you're going to be running that build 5 times, and it's going to get very expensive. And additionally, when you're using additive manufacturing in your product development cycle, again, just because it can be printed doesn't mean that it can be manufactured with a traditional process. So make sure that you guys are partnering with somebody that can help you with that design for manufacturability feedback early on in the process before you start prototyping, and you're going to have a much better chance for success with that. So I mentioned that there were dozens of different technologies out here. Today we're just going to take a little bit of a closer look at 2 of probably the most common technologies, which is Fdm and Sla, or fused deposition modeling, and stereolithography apparatus, which is what those 2 things stand for. So FDMs are typically like quick and dirty prints. They're very easy. There are dozens of printers out here that you could probably buy for a couple $1,000 that would actually allow you to use this technology and print on your desktop at home out of an actual thermoplastic. So the way that I like to describe the process itself is you basically have an extrusion nozzle that's laying down a thin filament of this material over and over, line by line, layer by layer. So if you can imagine looking at a spool of fishing line, that's kind of what the part's going to look like when you get done. So as you can imagine, there are some limitations that you have with this process. So if you can imagine creating a snap feature that's in the vertical direction of the build and you try to apply stress to that, it's likely going to delaminate, so it's not going to function exactly the way that you need to. So there are some cautions here that you want to take and make sure that you're working with somebody that has the experience to make sure that your part's built and oriented in the machine to print it appropriately. The process itself, though, for FDM is typically a lot faster than SLA. Not necessarily the build itself, but with SLA, you have a lot of post-processing that you have to do. You have to wash the parts, you have to clear the supports, you have to cure the parts again. So, and then there's additional finishing if you want a nice clean surface finish on it as well. So typically FDMs, you build the part, break away the supports or wash off the supports, and you have your finished part. With stereolithography, though, even though it does have some additional finishing that's required after the part's done, you can get really good dimensional accuracy and surface quality in the part. I've seen marketing models that have been used for photo shoots that have been basically finished SLAs where they're highly painted, highly cosmetic. They're great for those types of applications. And there are a wide variety of different materials that are available that do simulate real world materials that we're using in a lot of injection molding applications. But again, it's simulating, it's not the actual material, so there are some considerations there. And I mentioned earlier, it's also typically going to be a little bit slower than, totally missed my slide there, slower than the FDM process. So with injection molding specifically, often what we're doing with this technology is we're going to be using this for more complex parts. There's a lot of opportunity here for insert molding and over molding, which there are some technologies you can use for 3D printing to simulate those, but it doesn't give you the same real world applications that you get when you're actually molding these features in or doing a true second shot molding process. If your parts need high dimensional accuracy, or if you have specific testing that you need to do on the material, or drop testing or anything like that, typically you're going to look at using an aluminum tool to do prototypes out of the end material that you're going to be using, because that's really the only way that you're going to actually get an in-use part to be able to do those tests. Or if you're just doing some evaluation of what the part's going to look like, you want to look at shrink and warp and splay or aesthetics, like what the part's going to look like when it comes out of the mold. You obviously have to go with a process that's going to be very similar to what you're going to be using in a production environment. Or if you know that you have to run a large number of samples of the part for whatever application. So if you need 500 parts, typically making an aluminum tool for your prototype is going to be a lot less expensive than printing 500 parts, even if you don't need to do any of the testing that we talked about before. But with that, there are some cautions that you need to keep in mind. So obviously, you're going to have much higher upfront costs because you have to cut the tool before you can start running parts. Typically, it's a little bit longer than rapid prototyping. With rapid prototyping, obviously, you can get parts in a day or 2 days. Tooling, the fastest tools that we typically do are about 5 business days. So it's not a tremendously long time, but you do have to make sure you're taking that into consideration in your product development cycle. And there are obviously some design restrictions that you have here. So you have to have draft on all your features. There are certain undercuts that you can't accomplish in an injection mold tool or become very cost prohibitive. If you're talking about having to use hydraulics for certain cores or unscrewing cores and that sort of thing. So certainly things that you want to keep in mind as you're going through the design process. And also, if you get into a tool and you have to make changes to the design, it can be expensive. As I mentioned earlier, like if you're taking plastic away, there's not going to be a steel safe change. So you're going to have to add metal back to the tool, which either requires welding or recutting a new tool depending on the specific design changes that you're making. So that's going to add a lot of time and cost to your process up front. So what we see is that most customers are using a combination of both of these technologies together. The way that we're defining success for them is we're looking at total design process time, design process certainty, and time to market, which are all very important parts of the product development cycle. So oftentimes what we see customers using FDM for, again, very quick, you can iterate quickly, you can even buy a printer where you can do it at your desktop in a matter of a couple of hours. So it's great for your initial concept, maybe the look and feel of the design, maybe even some functional testing, depending on the features that you have built into the design as well. If you want more of like a higher fidelity part, better surface finish, better finishing options, SLA tends to be a little bit better than what we see with FDM. And also with SLA, you have a much, much wider range of different materials that are available. The difference being that FDM is using an actual thermoplastic, whereas with stereolithography, it's a simulated material to that thermoplastic that you're looking for. For what we specialize in at Xcentric is prototype and low volume injection molds. Typically we're using QC10 aluminum, we can do P20 steel as well, but usually this is great for when we have customers coming to us for the prototype element of the process. Usually this is for fit form functional testing, that they have to use the end product material in their testing environment. So this is a great opportunity. We can do it relatively quickly for them. And additionally, this is a great bridge tool opportunity if you are moving into a high volume class 101 mold that's going to take you months to produce. You can use an aluminum tool, get your actual end-use material relatively quickly, as fast as 5 days, and be able to use that to bridge the gap while you're waiting on your production tools to be completed. Production tooling, typically this is going to be class 104, 3, 2, and 1 molds. So usually you're looking at steel, P20 steel or harder, up to stainless steel in some instances, some coatings that you can have. So this is great. Like if you know that you need to run millions of parts a year, typically you're going to be looking at a hardened steel production tool or potentially multi-cavities that you want to do there. And we often work with customers at Eccentric where we are, again, bridging the technology to help support them while they're working on those specific tools that take months to produce using a prototype or low volume aluminum tool. Now taking a look at a couple of instances where we've worked with customers to be able to provide them, use both of these technologies to help them accelerate their product development cycle. So the first one, a customer had an idea that he wanted to present to his marketing team and his board for approval. And then after he got approval from his marketing team and board, he wanted to do some testing he was doing drop testing in this specific instance, so he needed the actual thermoplastic that he was going to be using in production. And then eventually it was going to be about a 50,000 shot per year program that he was going to be running. So what we did for him specifically is we used an SLA to get that in front of his board, in front of his marketing team, so that could be socialized and approved before we transitioned to an aluminum, single cavity aluminum injection mold. So because he needed to do the drop testing, we had to use the mold for the samples that we ran. We gave him 25 samples of the part, and then ultimately after that got approved and passed all the testing that he was doing, we were able to transition to his full production using that aluminum tool, and it was able to run for multiple years without any issues. So basically, why did we choose those technologies? Again, 3D printing, the SLA was a great opportunity to give a high fidelity, good surface finish part that he could get in front of his board. He could get the approval that he needed before we transitioned into the injection molding to serve both the prototyping and the production that they needed for that program specifically. The second case that I'm going to talk about is It's very similar, but there are some slight variances here. So again, needed something to get in front of his marketing team and his and the board to get approval on the program itself from the design and the concept that he had. And eventually they were going to be ramping to 10,000 parts per year. They knew that they were going to have a lot of design changes that were going to be coming up through the process as well because of the industry that they were in and what was happening. So what we did is we actually used the SLA for the socialization and the approval with his board and his marketing team. And then we created a prototype tool with the anticipation that we were going to have to make some changes to that tool. So we made it steel safe around those features so that instead of having to remove plastic from the part, we were able to add plastic to the part to really get it dialed in to what they were looking for specifically. And so we were able to make very small, easy changes to the tool, relatively low cost, relatively fast timing, comparative to having to build the tool from scratch. So again, the 3D printing was a low-cost opportunity to be able to socialize the ideas and the concept with his board and his marketing team, and the tool allowed us to go through the iterations that we knew that we were going to have to go through with this customer. And the last one I want to take a look at today is a customer that had already done their own prototyping in-house, and so they had already gotten the approval for the program. And their initial volumes were going to be really, really low. It was only going to be 50 parts for the first year, and that was going to ramp to about 25,000 parts per year after that. The challenge that they had, because the volume is really low, additive manufacturing or cashier thing may have been a really good option for that, but the environment that the parts were going to operate in was outside. It was going to be in a really rugged environment, so it needed to be needed to have a UV inhibitor added to it, and it needed to be out of an actual thermoplastic that was going to handle the rugged environment that they were in. So what we ended up doing for this customer was, since they had already done the rapid prototyping themselves, we cut an aluminum tool so they could do the testing of the initial year 50 parts that they needed, and then they were able to maintain that tool after everything was validated to be able to transition to their full level of production with 25,000 parts a year. So really, here, because of the material requirements, the only solution that was available for them was going to be injection molding, and we were able to do this in relatively short order to be able to accommodate all of their prototyping and production needs. So what do we look at what are the decision criteria that we have for your project? There are a few things that you want to keep in mind here too. You want to consider your immediate, your mid-range, and your long-term goals for the project. So what are your budgets? What are your budgetary requirements for each of those different stages? How fast do you need to get parts in hand? What are you going to be using the parts for? Is it going to be for demonstration? Is it going to be testing? Are there going to be expected or even potentially unexpected design changes that may come up in the process? What materials do you need to make the parts out of? And then what are your volumes going to look like for each of those different stages? So I encourage you all to work with a manufacturing partner that can basically walk you through that entire process, provide the design for manufacturability, advice that you need at the very front end of the process, and then support you through whether you're going to a full-blown production tool or not, be able to support you through each of the different stages, both immediate, mid-range, and long-term objectives that you have. So a little bit about Eccentric Mold. We've been around for about 25 years. We're based out of the Detroit area. We have 2 state-of-the-art manufacturing facilities making up about 70,000 square feet with 35 different presses that we're running, tons of different milling centers that we're using to cut all of our tools. We've made over 100,000 different molds to date. We're running thousands of different grades of thermoplastic resins based on the specific needs of the customer. And we are ISO 9001 certified and registered with ITAR, so we can support those types of programs as well. We do everything. Injection molding is our core process that we support, but we can also support CNC machining and rapid prototyping. Again, rapid prototyping has dozens and dozens of different manufacturing processes available there. We have a large network of partners that we work with to be able to support that as effectively as possible. So if you do have specific rapid prototyping needs, we can help you through every stage of the manufacturing process.